Hello students, today we are going to talk about the DC current flowing through LR circuit and what happens with it, how the current is regulated, what is the mathematical expression for that. We shall also define a new term known as time constant for LR circuit. Here we assume that we have a inductance and resistance connected in series, and across this we apply some EMF of a steady nature. Means this EMF is always unidirectional, as in case of alternating EMF we have seen that the potentials of the two polarity are exchanging after every half cycle. But in this case we have unidirectional flow of current, unidirectional flow of charge due to some DC source attached to it. Now we assume that I is the instantaneous current flowing through the LR circuit when we put on the switch. Now this applied EMF, if we take, is equal to E. If DC EMF of this DC source is E, then we can certainly take that the applied EMF E must be equal to potential difference across the inductance coil plus the potential difference, that is potential drop across the resistance of the circuit. So that means we can write EMF E is equal to L di by dt plus IR. You see, for inductance we already know that a potential drop across the inductance is L di by dt. We have learned it. And for a particular case, when you see the current in the circuit saturates after some time, and once this saturation takes place, then di by dt becomes 0, means there is no change in current, and for that value, for that case di by dt is 0, and for that case the current is maximum is equal to, say, we take it as I0. I0 we take as the maximum current, saturation current in the LR circuit. So in this case, if you have di by dt is equal to 0, this term vanishes. So EMF must be equal to saturation current, which we have taken as I0, into R. So we can write E is equal to I0 R. Now applied EMF is constant, so this is a constant. So if we write this equation, rewrite this equation, what we see that I0 for EMF is equal to IR plus L di by dt, where I is the instantaneous current in the circuit and I0 is the saturation current in the circuit, and L is the inductance of the inductance coil, and R is the resistance in the circuit. So if we rearrange it, you take IR on the left hand side, you get I0 minus I R as common, equal to L di by dt. Now if you rearrange it further, you can write di by I0 minus I equal to R by L into dt. You are rearranging this equation. So on integrating both sides, what you see is di by I0 minus I0 is a constant, so we get log minus log E I0 on doing the integration, we get minus log to the base E within bracket I0 minus I bracket close equal to R by L into T plus a constant which is known as, plus a constant K which is known as constant of integration or integration constant. Now from this equation, if we take t is equal to 0, in this equation if we take t is equal to 0, you see this term vanishes, and also at t is equal to 0 instantaneous current will be 0, that means I is 0, so we are left with k equal to minus log to the base E of I0. So we have k equal to minus and since this is a constant, k is equal to minus log to the base e I0, so, and since k is a constant, so we can substitute the value of k over here now and write this equation as minus log to the base e I0 minus I equal to r by L into t plus k value, that is minus log to the base e I0. Now you rearrange this equation, you see this, here we have log and here we have log. We change the side of this log, we get we get log I0, here you have a log I0 divided by log I0 minus I, so that becomes I0 by I0 minus I, and here you take it on the left hand side, this becomes plus log to the base e I0 and this is minus log to the base e I0 minus I, so that becomes log, together writing I0 by I0 minus I, and on the right hand side we are left with r by L into t. So now if we take the exponents on both the sides, what happens? This log vanishes with the exponent taken on this side, and on the right hand side we get exponential to the power r by L into t. Now if you rearrange this, you get if you invert it, you see you get I0 minus I by I0, you just invert it, it becomes e to the power minus r by L into t, where t is the time lapsed, r is the resistance, and L is the inductance of the coil. Now rearranging this, you have I is equal to I0 1 minus e to the power minus r by L into t. This is the expression for instantaneous current flowing through the LR circuit when some EMF E is applied across it, and if we put the value of t equal to L by R, then what happens? R by L into L by R becomes minus 1, so it becomes, the relation becomes I is equal to I0 1 minus e to the power minus 1. So we define a term time constant of LR circuit is that time in which the instantaneous current in the circuit increases, that time in which the current in this LR circuit increases to 0.632 factor of the maximum current. This corresponds to maximum current, the saturation current. So the time taken by the circuit to raise the current, instantaneous current, up to 0.632 fraction of the saturation current, that time is known as time constant, and that time will be equal to L by R. Now how come we get this value? Let us see. You see, if you write for t L by R, this factor r by L into L by R becomes 1. That means I is equal to I0 1 minus e to the power minus 1, and e to the power minus 1 can be written as 1 by e. I is equal to I0 1 minus e to the power minus 1, it can be written as 1 minus 1 by 2.718, that is the value of exponential e to the power 1 is having the value of 2.718. And when you solve this relation, means you take the reciprocal of 2.718 and subtract it from 1, you get 0.632. So time constant is that time in which the instantaneous current in the circuit becomes 63.2% of its saturation current, and that means this time constant depends upon L, proportional to L, and depends upon reciprocal to R. Greater is the inductance, greater will be the time constant. Smaller is the inductance, smaller will be the time constant. Greater is the resistance, smaller will be the time constant, and so on and so forth. So this is the behavior, this decides the behavior of time constant of the LR circuit. Well, you see, so if you happen to have a bulb attached to this place instead of resistance, then what will you see? What you will see is the bulb will start glowing with varying intensity continuously till the current saturates. So it means it will increase gradually. More is the current, more will be the glow, and it will saturate. It will become 63.2% of the saturation current in a time which is equal to L by R. So that's all for today. Thank you and have a nice day.